构是接到基本线。
Alright, so let's go to the fight number 2. And now the opponents want me to challenge the question to the reporter. Accept? Okay. So number 5. Okay. Problem number 5 is accepted. So on each team should write a representative on the platform.
第6题这一场刚刚有用过，应该不能用了。在这一场也不能用第6题。
那是第5。
那个刚刚已经有人报过了，这一场就这一场，这场第6题应该不能用。
他是第5题啊。
刚刚是第5题啊。
对，他现在做第5题。
手刚拿这边。
哦，你说上面。那可能要。 sample reporter.
Hello everyone, my name is Danielle Lee and I'll be presenting problem number 5, dancing slinky on behalf of the all-nighters. This is the problem statement. Twist the slinky several times and keep its bottom fixed. After releasing the top, the slinky starts to dance, which is a wave-like phenomenon that can be observed from the side view. Explain the phenomenon and investigate the parameters affecting the slinky's motion. We will be focusing on how does the slinky dance and what parameters impact the slinky's motion. This will be the flow of my presentation today. Onto the phenomenon investigation. The parameters that we will be looking at are the initial amplitude of twist, the number of coils, the mass, and the stiffness of the spring, which is impacted by the shape of the coil and its material properties. This is a demonstration of the phenomenon. There is a video here now. So we will define dancing as the slinky experiencing lateral shifts. The radius contracts slightly when tightened but stays constant when loosened. However, the contraction is minimal, so we will assume that the radius stays constant. We also observed that with a less amount of coils, there will be faster angular and lateral recoil. Now on to our theory. So our reason for lateral motion could be that each coil is relative to a point on the side that we've labeled, and the twist adds a stress which makes the system a torsional oscillator. We also think that the lateral movement results from the uncoiling motion. For a system of coupled oscillators, we have two equations that one relates to lateral motion, represented here. The other relates to angular motion, represented here. The kx in the first equation is derived from Hooke's law, and so is the gamma theta in the second. On to experimentation and discussion. Our experiment looks like this, where we set up a camera with a slinky, and we use tape to limit the number of coils that we're actually using, because the tape restricts the motion of the bottom one, so we don't need to take those into account. And we also labeled the sides of the slinky with a marker, which will be the tracking dots when we put them into tracker. And for testing the angle of movement, we twist the slinky to set the angles, and we use a top view camera and to record the angle between the centers. The reason behind the error bars for the red dots is because we draw the points using our hands, so it might not be exactly 180 degrees across. For a 62-layer slinky, which means that there are 62 coils, we only tracked the top 3 layers, and these results, the first graph represents the lateral motion, and the second graph represents the rotational velocity of the top layer. And as you can see, the peaks occur around the same time, which support our claim that the lateral motion and angular velocity are related. Now, moving on to our conclusion. So, our conclusion is that the slinky acts as a coupled oscillator with a rotational motion resulting in lateral motion. Our plans for future work could be to control friction to determine how the interaction between coils impacts the acceleration and velocity. We could also increase the number of trials to account for more error. And in the future, we could relate torque directly with lateral force and acceleration because currently we have two separate equations for those. And regarding the less number of coils resulting in faster angular and lateral recoil, a possible explanation for that could be with less number of coils, the torque and lateral forces are less spread out, therefore act on therefore there's less force. There's more force. Now, accounting for errors, we assume that the radius does not change because it's minimal. However, small changes could possibly result in some error. There is also human error in the experiment because the slinky is twisted by hand and released by hand. And also the dots that we use to track the motion of the slinky are also drawn by hand. And humans are not perfect, so there would be error in that. Additionally, we did not account for friction, and the force of friction could apply some extra force that influences the net torque experienced by the slinky. And by friction, I mean the friction between the different coils when we twist it. Okay, that's the end of my presentation, my report.
All right, so it's time for the opponent to raise a question to be quoted.
I'm the opponent from variable 2. There's some question. Can you turn to the problem statement page? So you focus on why did the slinky this, and you want to investigate the parameters that affect the slinky's motion. Yeah? Is that right?
Yes.
Okay. So you do the experiment to like the experiment is connected to your parameters. Is that right?
Yes.
Yes. So how many experiments do you do to get the evidence to support your assumption? Okay. How many experiments do you do to support your assumption?
We could define that as one.
Okay. Next. I think I will discuss later because I think it is unclear or there's some misunderstanding of myself. Yeah. Okay. Please turn to the page 9.
9?
9. Yeah. Okay. Is there any connection to your experiment to your formula? Because I can't find any connection of your theory and your experiment.
Oh, this will be on this page because as you can see, the top layer's rotational velocity is correlated to the lateral motion.
Okay, so I think I will like have to ask about why is there difference between the two pictures in the discussion.
All right, so the preparation time for the 3 minutes to prepare. Okay. Following detect all of the following.
Okay, let's start. The problems, the phenomenon is set up. I'll first talk about the problem statement. They say that, they mentioned that they want to find out the parameters that affect the slinky's motions. But I don't find, isn't that I didn't saw a lot of parameters that will impact on slinky dance in their experiment. So I think I will discuss with them later. They have a good accent and they have a great demonstration, but their concept not familiar with the report and the experiment, and they aren't enough in the content, and too much word but not enough graph and unclear graphs because I can see the x-axis and the y-axis. And this is a therapy. Initial amplitude of twist, numbers of coils. But I think that they look the slinky from the top. They didn't see in the side. But I think the tennis slinky's definition is to observe the slinky from the side. So I think I'll discuss with them later. This is an experiment. The dancing slinky experiment later, lateral shifts. It's an assumption. They did several assumptions, but small changes can cause a lot of difference between the experiments. So I would like to ask about them later. And the experiment system of coupled oscillators. And to the later slinky on the page 30, I think they should explain the graph further because just like what I say, they didn't explain it well, and they didn't do the connection to the theory and their chart or even their experiment. And they have several errors, but they don't try to they didn't try to solve the error. So, but I think some errors can cause a lot of difference between the experiments, such as damping force. So I think this will be an impact on their experiment. And this is the conclusion. The slinky acts as a couple of oscillators. Rotational motion results in lateral motion. Enter the discussion. They use hands to twist. I think it is inaccurate. And they use camera accurate. I think camera isn't accurate enough. So I think I will discuss with them later. And how did they measure the motion? I didn't very clearly know how they measure the motion. And I want to ask that what caused the error? And that's all.
Okay, so discussion time. Reporter.
Firstly, I want to ask about what's the definition of dancing slinky? Because it seems that you look the dancing slinky from top, but not on the side.
In your presentation just now, you asked if my definition of dancing as the slinky moving laterally was an assumption, right?
Yeah.
But that's just really our definition of what dancing means in the problem statement.
So the definition is how does this encircle?
No, laterally.
I'll draw it on the backboard.
like this, it will stick regularly, and when it shifts, this is when.
So you're just talking about from the side, not from the top.
No.
Okay. So I want to look at your picture that you have the photo of the sinking. I want to look at the picture. This one? Yeah. So you use the camera to take the video after sinking? Yes. Or no? Okay. Is that accurate enough? To use the camera to film the video. Yeah. How do you share that?
How do I want?
Ensure that it is accurate.
What is the definition of insurance?
Because sometimes camera can't totally film the whole motion of the sinking. And even it is accurate, you can clearly know how does it move in the like tiny region.
Oh, we use two cameras.
Oh, you too.
One is on the side and one's on the top. That's why we're able to both
So
measure.
there's no picture to film the sinking on top.
I didn't put it.
Okay. I think you should put it because it will have some misunderstanding about that. Okay, next question. Can you turn to the page that you talked about the parameters that affect the sinking motions? So can I see the experiment that refers to the parameters in your report?
The experiment.
Yeah, to support your parameters.
We might go for which one?
Experiment. Next. Okay, this one? Oh, yeah. What do you want to say? What do you talk about in this experiment or in the chart?
I mean, what is the purpose of
Yeah.
this one? So the purpose is just to show the correlation of how the correlation between time and these two different components, because when they oscillate, which is why I included time, the general shape is the same, so that's why it's interesting that it's correlated.
So what did you want to talk about between the two charts? Because there's no connection between your theory and your experiment. So can you explain what did you want to talk about in the chart?
In the chart? Okay, so this one is the oscillation of when it's moving side to side, and the other one is the top layer. It's like one view from the top, so you're looking at rotational velocity.
Rotation velocity? Or rotation velocity of the top. Turning to the page 11. You use tape to make this stable. Yes. How to ensure that it is accurate enough? Because it said that this will be stable and it can move. But you use tape to tape it. I don't know if there's any like variation in the behind the tape. Because you use the tape to make it stable. I can find that I can know that if there's any variation in between behind the tape. Because you use the tape to like cover it, so I can see it clearly. You have to like explain it for me.
Okay, so we also wrapped it inside to ensure.
From inside to ensure. So how does the sinking move inside?
It doesn't.
It doesn't. So you just observe the sinking above.
Yeah, the whole point of using tape is to limit is to know for sure the number of coils that we're using.
But if you just observe the sinking above, this one will be fixed. You want to make make the bottom of the slinky stable. But you take this and observe this. So the bottom of the slinky will be here. Here won't be stable, right? Why?
Because we're including that one as fixed with the tank.
So how did you include that?
That's like one.
Because you say this is stable, but when you twist the slinky, it won't be stable, yeah? Because they won't move.
Are you talking about the last coil that needs to be stable?
Yeah, because the below one will have to be stable.
Yeah. So I put it within the chain so it doesn't move.
How did you know that it didn't move? You filmed the video to ensure that?
Yeah.
But I don't think this is the proper way to ensure, because you can't really know that if it definitely moves.
Do you mean like you can't observe it?
Yeah, you can observe it.
Oh, I see. That could also be a possible.
Okay, so I think this arrow it will have a large impact on your slinky, because according to the problem statement, they say that the bottom of the slinky might have to be stable. So you do the kind of experiment. I think the last of the experiment isn't accurate and appropriate things to report to everyone, right? Because it is inaccurate, and what we want to observe will be inaccurate because of this, right?
It could be. It's just not a high possibility that would happen.
And is there any accurate data in your experiment?
Accurate data?
Yeah.
To
Support your chart. Is there any data?
my chart.
So this is the data in your experiment.
Yes, that is data.
And can you explain why does it be like this?
I did not investigate why it looks like that.
So it's not because of the formula above. It's not. Right? It's not because of the formula above. So the chart is not to the aim of the chart is not to support the formula above, right?
The whole point of the shape is to show like the oscillations of the lateral motion
So why is there like this?
because it shows oscillations.
So why does it? Is there any evidence in the formula? You prove it.
No.
So there's no connection between your experiment and formula, right?
There is.
But you can't explain it, so there's nothing. Okay, let's turn to the next one. You say you have some arrows, right?
Yeah.
But-
You want me to turn that?
Yeah. Yeah. As these arrows have a small impact on your experiment or a huge impact? Would you investigate that?
For the radius one, we believe that it will not impact that much because the radius size changing is not very significant.
But here you say that small changes could possibly result in an error.
I'm saying small error because you asked
Yeah.
to what extent, right?
Yeah.
So I'm saying small changes could lead to small error, but it's not very big.
Is there any experiment or some theory to support this? Because it is your thought. Is there any supportive reason to support this? Or to
Oh,
prove it?
okay, it's time's up. So opponent. So opponent, you want me to summarize the discussion? 1 minute.
due to the discussion, I found that there are several errors, but they didn't measure it, and they do the kind of conclusion by their own thoughts. So I think it is not an appropriate way to do the business experiment. And to explain the two charts more, because they didn't talk about the XY axis, and there's no connection between their theory and their experiment. And yeah, so I think it is not persuasive. And they say that they use the tape to make the bottom of the slinky stable. But due to the purpose statement, it is not correct, because the purpose statement says that the bottom should be stable. But they use the tape, and they can sure that the slinky above will be what purpose statement wants us to do. So I think there may be some misunderstanding due to their experiment and their.
So now the reviewer can ask question to both our reporter and opponent.
So questions to the opponent, can you turn to page 13? Yeah, so the right graph, the title of it is the rotational velocity, but the y-axis is the x. So can you give an explanation about that?
Oh, wait, are you asking opponent?
Report.
So this entire graph is talking about velocity, but because velocity is it's a mislabel.
So it's just a mistake. Okay. Same page. So from the equation above, you can see that there's a kx formula. So, but since the equation of f equals a kx is usually used in in extension or compression. So can you give a brief explanation on the formula above, the kx one? And same question for the opponent as well.
Oh, so the kx is from Hooke's law. I think you already know that, but we've rearranged the equation, so that's why it's not a negative. That's why it's not a negative sign. And for stretching and compressing, since the slinky is sort of a spring, that's where yes.
I can totally believe the formula because I can find the evidence in the experiment. But I guess that the kx, it might be the kinetic energy in their experiment because the slinky will move.
Okay, thanks. And can you turn to page 16? So questions also for both the reporter and the opponent. So as the reporter mentioned, the radius might cause some error in the results. And do you think is it a positive deviation or a negative deviation on the experiment result?
I really need to think about that.
Can you repeat the question again?
So the reporter assumed that the radius is fixed, right? So, but they say the small changes might cause some error in the results. And what do you think about the error? Is it a positive deviation or a negative deviation?
I think it's a negative deviation because they want to find the connection between the stable radius and their result.
Okay, thanks. That's all my fault.
Right. Now is the preservation time for the video. 2 minutes. Reviewer can take the floor.
Okay, so this is reviewer from Mindanao High School, and today I'll be reviewing problem number 5, the Slinky. So here's a problem statement, and the main focus for the reporter is how does the Slinky dance, and the parameter that affects the Slinky's motion. And this is the review of the report. So in their presentation, they investigate the phenomena and make some assumptions, such as the radius is stable. And the theory, they use a system of coupled oscillator and the reason of the lateral motion. And in experiment, they tested the angle of the movement, which is also referring to how the Slinky dance. And also they do experiment on investigation of the 62 layers of Slinky. And their conclusion is that it acts as a coupled oscillator, and the rotational motion results in lateral motion. And they also based on assumption on the possible errors. And I think the reporter has some very clear observation on the phenomena, and also they elaborate some possible errors in the experiment. But our suggestion for them is that they could have more explanation on the data, and maybe they can compare their theory and their data with some theoretical data. So, and here is the review of the opponents. So we think that they have a sharp and well-constructed criticism, and they have good engagement in discussion. But our suggestions that maybe they shouldn't be too much aggressive or dismissive on their opposing, and they have to take more care on the time management. So here's the review of the opponent's question. So the first question opponent asks is that the reporter used camera to film the phenomena, and is it accurate enough? And the reporter says that they use a camera on two sides to make sure that. And our suggestion is that we think a more clear setup would be better. And here's the discussion about the definition of dancing. So the opponent asks if the reporter observed the phenomena from the side. And the reporter says that they only observe the phenomenon from the top of the Slinky, and it is inert. And we agree both on opponent's points, and we only agree on the both. We think both sides of the observation is needed. And here is a discussion using hand, and the opponent thinks that if you use hand, it's not accurate enough. But and the reporter doesn't answer, but we think that it might contribute to some errors. And here's my question on the kx in the equation, and the opponent thinks that it stays for the kinetic energy, and the reporter says that the motion also satisfies Hooke's law. And our next question is the deviation, and the opponent thinks that it is a negative deviation, and the reporter doesn't answer. So here's the point missed, we think. So first of all, they missed some parameters such as the diameter of the Slinky, and they have unclear elaboration, and our experiment is comparative since they don't have clear demonstration video. And that's all my review for the presentation. Thank you.
Then the reporter, you have 2 minutes to conclude. Reporter.
So for conclusion, we believe that we have completed sufficient trials for our parameters, suggested by our graph here. The different colors represent the different trials that we took. In regards to the opponent's view opinion on the top view, it is a worthwhile point of investigation for lateral motion lateral motion because we can also see it shifting to the side through the top, and will also negate some of the errors caused by the effects where the camera angle will impact how far the slinky goes. And in regards to our graph, the correlation between this is that they both show dampening oscillation, and that is why we believe that those two are correlated. The lateral motion and the rotational motion are correlated. And now I'll move on to I'll answer the reviewer's question about where the KX come from. That is the restoring force. So within that is representing the restoring force.
Okay, time's up. So now it's time for question from viewers. Any questions?
I heard before you three mentioned about the coupling. Could starting from the reporter and then the reviewer and the opponent. Could you explain what kind of motion we cover? Is there only the twisting or rotation motion and the lateral motion?
In our experiment, that is what we're testing, that the coupling between the lateral motion and the rotational motion.
Is there any more web back up and down in your experiment?
We were not testing that aspect.
Any comment from the other two?
So I think there's a open definition on how the tensing, but I think the reporter, when they do the experiment, they only focus on the horizontal direction, but there might be also some vertical motion that may be leading to more energy loss or some perturbation in the parameters.
There are also damp harmonic motion, and also when you twist the string, it will like this and go like this. So and also their light will rotate. So there's three kind of motion.
Thank you.
Can I elaborate? During our experiments, we did notice slight vertical wave motion. However, because that was not our focus, we did not put that into very easy consideration.
Other questions?
So question to the reporter, can you turn to the page of your data? Can you tell me what does A stands for?
Oh, the A stands for, it's like a constant.
Sorry?
It's a constant.
Constant.
Does that satisfy your question?
Just want to know what does it mean?
Oh.
Yeah, and then, okay. So back to your theory, the model. Okay, here, yeah. So just make sure what is the last three equations, the meaning of, yeah, the last
Oh, this is
last
just,
three.
these three?
Yes.
Okay, so this is just a derivation for the last line, which is the equation that we're actually using. So it's relating torque with the restoring force and the dampening force.
So R is the radius.
Oh, that is gamma.
Gamma, and D,
That's the dampening.
damping. Just make sure. Any other?
So as still wonder, did you twist the slinky more than one turn, or just for 30 degrees?
Oh, we did twist it multiple angles.
Just for how many degrees did you twist it? Or maybe more than one turn? You twist it many turns before you release it?
Yeah. But this is just like an example of what I'm talking
All right, well, I just feel it's kind of hard to define your initial angle.
about.
I mean, you didn't specify the initial turns, the number of turns you twisted, right?
Yes, that is.
Okay, that's all right.
So it's time. Any other question? Okay, so it's time for George to. Okay. Next time, that's for recorder. 45443. Now it's component. 66656. Okay. And now finally for the reviewer. 77766. Okay. Wrap up is 5. Okay, anyone? George, comment? No?
A short comment to the reporter that you prepare the experiment, that's nice. It's just a pity that you don't show much data, you don't change many parameters. And I believe that you mentioned the key point in the picture, sounds like a critical point, right? Because the picture is too large, so the damping decay, oscillation decay very fast. Probably this is the critical point. So that's all. I also say that 5 is average. So just because you don't provide sufficient data, it doesn't mean that your work is not so good. I would say.
Okay, so let's take a 15 minutes break.